Good morning, students. Today we will discuss about to find out the area of the region bounded by the given curves. Suppose we have a function fx is a continuous function defined on the interval closed interval ab. Then the area bounded by the curve y is equal to fx, x-axis, and the ordinate x is equals to a and x is equals to b is integration a to b y dx. The area bounded by the curve x is equals to fy, y-axis, and the abscissa y is equal to c and y is equal to d is given by the formula a c to d x dy. So these are the two ways by which we can find out the area bounded by the curves and the x-axis or the y-axis. As we already know, the regular figures we know the area, but if the figure is not regular, then we can find out the area using the integration. Now we take some examples to explain how to find out the area of the various curves. So we consider the following case. First we take the area of the bounded by two intersecting curves y is equal to f1x and y2 is equal to gx, and the ordinates x is equals to a and x is equals to b is given by the formula a to b modulus y1 minus y2 dx. We take one example to explain further. Suppose we have to find out the area bounded by the curves x square is equal to 4y and the straight line x is equals to 4y minus 2. The curves are given as x square is equal to 4y, so we can calculate the value of y is equals to x square upon 4, and the line x is equals to 4y minus 2, or we can say y is equal to x plus 2 upon 4. So first we need to find out the point of intersection of the curve. So we solve the equations and we get the intersecting points as x is equals to minus 1 and x is equals to 2. So the points of intersection will become minus 1 comma 1 upon 4 and the second point is 2 comma 1. After that we will draw the figure of the region which we need to find out the area. So we will shade the region which is to be found. Now here we find out, if we have to find out the area bounded by the x-axis, then that is limiting from the intersecting point minus 1 to 2. So this can be expressed. The equation of the shaded region, we can say that minus 1 to 2 y1 minus y2 dx means upper curve minus lower curve. Now we will substitute the values of y1 and y2 to the values and we get x plus 2 upon 4 minus x square upon 4 dx. So we will integrate and substitute the values, and after that we will get the area, that is 9 upon 2 square units. So this way we can find out the area between the two curves bounded by the lines and the parabola. Now we consider another example, that is the area of the region which is bounded by the ellipse and a straight line. Once we draw the diagram, we will find out there are two possible areas by which we can find out between the straight line and a ellipse. But here it is mentioned that we have to find out the smaller region of the curve. So we have the two curves, ellipse x square upon 16 plus y square upon 9 is equals to 1. We will find out the value of y from this value, that is 3 under the root 1 minus x square upon 16. Similarly, the straight line is given x upon 4 plus y upon 3 is equals to 1. From this also we will find out the value of y in terms of x. Now we will calculate the point of intersection of the two curves. Solving these two equations, we get 4 comma 0 and 0 comma 3. Now we will draw the diagram, ellipse and the straight line. We will shade the region which we have to calculate the region area, that is between the ellipse and the line, that is the smaller area which we need to find out. The required area is the area of the shaded region. It is from the limit 0 to 4 y1 minus y2, that is ellipse minus straight line, and we'll substitute the values y1 and y2, we'll integrate it and ultimately we'll get the area using the formula, and the answer will come. That is 3 bracket pi minus 2 dx. Here we have to remember the formula under the root a square minus x square, which is applicable in both the cases, circle as well as ellipse, and the simple integration formula x to the power n that we have to integrate. So this way we can calculate this area also. Now we take another example to further strengthen our concepts. We have to find out the area between the parabolas. Parabola y square is equal to 4ax and another parabola x square is equals to 4ay. The same process we have to do. We'll calculate the value of y from y square is equal to 4ax, and we'll calculate the value of y is equal to x square upon 4a from the second equation. We need to find out then the point of intersection of the two parabolas, and we get x is equals to 4a and y is equals to also 4a. So once we get the equation or the point of intersection of the parabolas, then we will trace the curve to find out the area which we need to calculate. This way we can draw the parabola, one symmetric about x-axis, another one is symmetric about y-axis. Where these two parabolas intersect, that is the point 4a comma 4a. And now we can find out the area of this region, that is the shaded region. Now we'll formulate the value. So first of all we will represent it in the form of integration. The required area is the area of the shaded region right from 0 to 4a y1 minus y2 dx. We will substitute the values of y1 and y2 and we will integrate, substituting the limiting values, and we get the answer 16 upon 3 a square units. Now, to further strengthen our concepts, we take another case when we have to calculate the area between the circle and the parabola. For this we consider a curve x square plus y square is equals to 16 and the parabola x square is equals to 6y. Find the area bounded by the two curves. So first of all, the point which we need to find out, the given curves, we know that. We will substitute the values in terms of y, both the curves, and we will calculate the point of intersection by simplifying these two equations, and we get the points. The points which we are getting, that is y is equals to 2 and y is equals to minus 8. After that we will draw the diagram of the curves and we can find out the area of the region. Now, another example, find out the area between the two curves. These two curves are circles. One circle when center is at the origin 0, 0, but another point the center lies on x-axis. One circle is x square plus y square is equals to 1. Another circle x minus 1 whole square plus y square is equals to 1. The equation of the circles are given. We will calculate the value of y in terms of x under root 1 minus x square. Another we will also find out the value of y under the root 1 minus x minus 1 whole square. Then we will equate them to find out the point of intersection between the two circles. We get 1 upon 2 comma root 3 by 2 and 1 upon 2 comma minus root 3 upon 2. After that, the same we will draw the diagram of the two circles and we shade the region which we have to calculate the area. Here we find that the shaded region is divided by the line in two equal parts. The limiting value, if we observe, it will be 0 to 1, one circle, 1 by 2 to 1 is another circle. So this way we will express this equation in the form of a integration. We will write 0 to 1 upon 2, first circle with the center 1 comma 0 and then 1 upon 2 to 1 with the center 0 comma 0. Both the areas we will find the values and add them. Since it is symmetric about x-axis, so we will double the area and we get the area of the required portion, and then we can calculate by substituting the formula and substituting the values, and we get the answer, that is 2 pi upon 3 minus root 3 upon 2 square units. The area of this circle, if we check, Another way to find out or to calculate the area using the circle is this line. If you observe, in 4 parts it is divided, and all four parts are equally having the shaded region, equal areas. So this can also be found that if we find out the area of one portion, either from 0 to 1 upon 2 or 1 upon 2 to 1, the single portion, if we calculate the area and multiply by 4, the same value we will obtain the area of the two circles. So this way we can calculate the area of the shaded regions, or the regions which we have to calculate the non-regular figures. If the figures are regular, we can easily calculate, but if the figures are not regular, then bounded by x-axis, bounded by y-axis, or the area between any two curves, we can calculate easily using the integration. Therefore, the chapter is known as Application of Integration. Similarly, if we have 3 lines which form a triangle, then also we can calculate the area using the 3 lines, area between the 3 lines that form a triangle, and using the formula of integration we can calculate the area of that triangular portion which is bounded by the 3 lines. So this way we come to know that using the integration easily we can calculate the area of the figures either bounded between the 2 curves or between the 3 lines, or the different figures like circle and circle, parabola and parabola, parabola and line, line and a circle, ellipse and a line, ellipse and a circle, between the 2 parabolas, parabola and the circle. There are the different figures by which we can calculate the area of the shaded region. So this way we complete this chapter, and thank you very much for your support. Thank you.